In this videotape, we will learn how to solve nonlinear systems of equations. In particular, we will be dealing with systems of equations, two equations where at least one of the equations is nonlinear of second degree. Okay, let's start with an example. Say we want to solve the following system of equations. Y equals x squared minus 4, y equals x minus 2. From earlier videotapes, we know that we are dealing here with a parabola and a straight line. Okay, the graph of this equation would be a parabola, the graph of this one would be a straight line. We can solve these systems of equations either algebraically or graphically. Of course, a graphical solution is not going to be terribly accurate. Okay, but it can give us a rough idea of where the solution should be. Okay, let's make a sketch of what's going on here. We have y equals x squared minus 4, which we recognize as a parabola. Notice that x is squared, y is not squared. If you have trouble recognizing these curves, I suggest you go back to an earlier videotape where we learned how to sketch lines, parabolas, circles, ellipses, and so on. Okay, the easiest way to sketch this parabola would be to get intercepts. If x equals 0, y is equal to minus 4. If y equals 0, x squared minus 4 equals 0, x squared equals 4, x is equal to 2 and minus 2. Okay, so here we have the parabola. Now over here we have a straight line. Once again, using intercepts, 2 points, of course, determine a straight line. If x is equal to 0, y is equal to minus 2. If y equals 0, x is equal to 2. So the straight line goes through these 2 points like so. Now we are looking for all points, x comma y, that satisfy both equations at the same time. So we see over here we would expect 2 points of intersection, 2 solutions to this system of equations, since the line cuts the parabola in 2 spots. Okay, now in this particular example, it's sort of easy to read this one off. Here we'd have a little more difficulty trying to actually read this off exactly from the graph. Okay, let us try now to solve these algebraically. Now, when you solved systems of linear equations, you had 2 methods. The method of elimination, aside from the graphical method, you had the method of elimination and the method of substitution. Okay, the method of elimination is not suitable when you have a second-degree equation and a first-degree equation. But the method of substitution is the one that we're going to use. Okay, what we have is y equals x squared minus 4, y equals x minus 2. We will substitute this value for y into the first equation. Let's do that. Okay, replace y in the first equation by what it's equal to in the second equation, namely x minus 2. So we'd get x minus 2 equals x squared minus 4. Okay, let's subtract x from both sides of the equation and also add 2 to both sides of the equation. One thing at a time, let's subtract x. This gives us minus 2 equals x squared minus x minus 4, and then add 2 to both sides of the equation, giving us 0 equals x squared minus x minus 2. We have a quadratic equation here, and we can have at most 2 real solutions to this quadratic equation. This particular one can be solved very simply by factoring. Of course, if you cannot solve your quadratic equation by factoring, you can resort to the quadratic formula. We'll do that in a later example. Okay, we're trying to factor. We'd like 2 numbers which multiply to minus 2 and add to minus 1. So we'll use minus 2 and plus 1. Checking by FOIL, we have x squared plus 1x minus 2x. That's minus x minus 2. Okay, if the product of 2 numbers is equal to 0, then either the first number, x minus 2, is equal to 0, or the second, x plus 1 equals 0, giving us x equals 2, x equals minus 1. Okay, as the x values. Now we're interested in finding the y values. These are the points of intersection of these 2 curves. We're trying to solve these equations simultaneously. Okay, now substitute into either equation. Let's say we substitute into the line. If x is equal to 2, y equals 2 minus 2, y is equal to 0. If x is equal to minus 1, y equals minus 1 minus 2, y equals minus 3. So we believe we have found the 2 points of intersection for these graphs, or the 2 solutions to the system of equations. Okay, now let's see if it makes sense. We have 2, 0, which is certainly this point over here, and minus 1 minus 3 corresponds to this point here. Now, of course, you should check your solutions in both equations, okay? Every solution point, or every possible solution point, should be checked in all of the equations, in each of the equations of the system. So let's look at 2, 0. Here, if x equals 2, y equals 4 minus 4, y equals 0, that's correct. Here, if x equals 2, y equals 0, that's correct. Now let's try the point minus 1 minus 3. If x equals minus 1 squared, that's plus 1, minus 4, that does give us the minus 3. And here, if x equals minus 1, y equals minus 3. So the points check out in both of the equations. Okay, so this system of equations has 2 solutions. We see it algebraically. We also see it graphically. Let's try another example. Let's use the same parabola that we had before, y equals x squared minus 4, but now let's use the line y equals minus 4. Here's, once again, a system of equations. At least one of the equations is second degree. They were both first degree. It would be a system of linear equations. We've already learned how to solve those. Okay, let us solve by substitution. Substituting y equals minus 4 from the second equation into the first equation, we get minus 4 is equal to x squared minus 4. Adding 4 to both sides, 0 is equal to x squared. It's a quadratic equation, but of course the only real solution is x is equal to 0. This is x times x. Okay, so x equals 0 is the only solution. When x equals 0, you substitute in here, you see y, of course, is equal to minus 4. If you want to make a sketch to see what's going on here, and why we only got one point of intersection in this case, it's very easy to see. This is the same parabola we dealt with before. When x is 0, y is minus 4. When y is equal to 0, x squared is 4, x is 2, and minus 2. It's this parabola. Line y equals minus 4 happens to go right through the turning point of the parabola, right through the vertex of the parabola. It's, of course, a horizontal line. Let me sketch it a little better here. Here is y equals minus 4. This is y equals x squared minus 4. We see that the line cuts the parabola in only one spot, namely at the point 0, minus 4. Okay, when you have a situation here where the line cut the parabola in 2 spots. Okay, you can have 2 points of intersection for such a system of equations when you have one linear and one second degree equation. You can have the line cutting the parabola, say, in one spot. Or you could have the line missing the parabola altogether. For example, we could have had the line y equals minus 5. And when you tried to solve these simultaneously, you would have gotten here minus 5 is equal to x squared minus 4. You would have had x squared equals minus 1. There would have been no real solutions to the system. Geometrically, this would be indicated by the fact that the 2 graphs do not intersect at all. Okay, how about x squared plus y squared equals 16, and y plus 2x equals 8. Once again, a second degree equation and a first degree equation to be solved simultaneously. Making the sketch sometimes gives you some degree of confidence. Okay, before you get to the algebraic solution, you sort of know how many solutions to expect, and this makes you feel good when you actually find them. Okay, so let's make a quick sketch of the system here. The first equation, of course, is that of a circle. Circle with center at the origin and radius 4. something like that. The second equation, of course, is out of a straight line. Using intercepts, if x is equal to 0, y is equal to 8. If y equals 0, x is equal to 4. So it looks something like this. And we see that we would expect 2 points of intersection. The line is cutting the circle in 2 spots. One of them is sort of easy to read off. We expect that 4, 0 would be a point here, and on that one as well. Of course it is. The other one is not that obvious. Okay, let's go about solving this by the method of substitution. The easiest thing to do would be to solve the second equation, say, for y, get y equals 8 minus 2x, and substitute that back into the first equation. The second equation gives us y equals 8 minus 2x. And we will take that and substitute it back in here. So let's see what we get. We have x squared plus y squared equals 16. X squared plus 8 minus 2x squared equals 16. And substituted in the value for y, 8 minus 2x. And now we're going to actually square this. This is really 8 minus 2x, of course, times 8 minus 2x. So you can use FOIL, and you would get first 8 times 8, 64. Outer is a minus 16x, and the inner is minus 16x for minus 32x. And the last is plus 4x squared equals 16. Collecting terms, like terms, we have 5x squared. That's from the x squared and the 4x squared. Minus 32x plus 64 equals 16. You can subtract 16 from both sides of the equation and get plus 48 equals 0. So what I did here was x squared plus 4x squared, that's 5x squared, minus 32x, then subtract the 16 from the 64 to get the plus 48 over there. Okay, now we have a quadratic equation, and of course our success in this problem is directly related to how our ability to solve a quadratic equation. Of course, if you are unfamiliar with methods for solving quadratic equations, we do have a videotape for you to look at. Assuming you do remember factoring, okay, this can be factored without too much difficulty. You wouldn't know, of course, by looking at it whether or not it could be factored, but if you try a few values in here, 5 can only be made by 5 and 1, so that's not so bad. 48, of course, can be made in a variety of ways, and you really would have to sort of make a little table and go through the possibilities, but this happens to work. 5x minus 12 and x minus 4. Checking it by FOIL, 5x squared minus 20x minus 12x is minus 32x plus 48 equals 0. Okay, now I don't want to make this seem that this, is just obvious, okay? The 5 has to be 5 and 1, but 48, of course, can be, has a variety of factors, and you'd have to really try all the different. Okay, we set each factor now equal to 0. We get x equals 4 here, 5x equals 12, x equals 12/5 here. And we need to figure out what the y values are. Okay, I find it easiest to substitute into the line y equals 8 minus 2x here. If x equals 4, of course, y equals 8 minus 8, y equals 0. That's very simple. If x equals 12/5, I get y equals 8 minus 2 times 12/5. That's not that obvious. You have to work it out. 8 minus 24/5, which is, now 8 is really 40/5, minus 24/5, giving us 16/5. Okay, so we get 16. Okay, so we solve simultaneously by substitution. We get a quadratic equation in x. In this case, there are 2 real solutions. We then substitute in each value into the line here. It's just easier, of course, than working with the second degree equation here. if x equals 4, y has to be 0. If x equals 12 fifths, you get 8 minus 24 fifths, 40 fifths minus 24 fifths, or 16 fifths. Okay, you should then check these in both of the equations. Okay, in the line, of course, we get 0 plus 8 equals 8 for the 4, 0. And 4, 0 here we get 16 plus 0 equals 16. That's no problem. In the 12 fifths, 16 fifths, we get 16 fifths plus 24 fifths. That's 40 fifths. That's 8. We've just worked that out. On the x squared plus y squared equals 16, we'd have to actually write that out. X squared plus y squared equals 16. X is 12 fifths squared here plus y, 16 fifths squared, should be equal to 16. We have 144 over 25 plus 256 over 25 should be equal to 16. That is 400 over 25 should be equal to 16, and that comes out to be 16. So it checks out. Okay, and looking at our graph, we see that the 4, 0 that we got, okay, corresponds to this point. And this point is a little over 2, comma, a little over 3, and that corresponds to 12 fifths, comma, 16 fifths. Of course, you would be hard put to read the solution off from the graph. The graph is not that accurate. Okay, but it certainly does look. This is 2 2 fifths, comma, 3 1 fifth. Seems about right. Okay, now I am aware of the fact that some of you do have a lot of trouble going from this step to this step. Okay, I don't want you to feel that if you can't factor, you can't possibly solve, systems of equation in this form. You can, of course, always rely on your quadratic formula. For those of you who find this helpful, I want to solve this particular equation by the quadratic formula, just to remind you how it works. Of course, if you need more detail, I would suggest you go to see that particular tape. Okay, it was 5x squared minus 32x plus 48 equals 0. Okay, let's say your factoring is really not in the best possible shape, and you would still like to solve the system of equations, so you need to solve this quadratic. Ax squared plus bx plus c equals 0. We match it up to that. And the quadratic formula, of course, is that x is equal to minus b plus and minus the square root of b squared minus 4ac over 2a. We have to realize that not every equation that results from, say, using the method of substitution on two equations is necessarily going to have a real solution. This particular problem could factor, but if you get one that doesn't factor, you could spend an awful lot of time before you've come to the conclusion that you can't factor. Okay, the quadratic formula, of course, could give you this information rather quickly. Okay, let's see what we get. We have here a is equal to 5, just matching up the coefficients of x squared. B is equal to minus 32. C is equal to 48. Okay, so we get x equals minus b, that's minus or minus 32, plus or minus the square root of b squared, that's minus 32 squared, minus 4, a which is 5, c which is 48, over 2a, 2 times 5. Okay? It requires a little bit of arithmetic, but at least it's a surefire method. Minus and minus 32, that's 32, plus or minus the square root of. Now, if you were minus 32 squared is the same as 32 squared, that comes out to be 1,024 if you go over the side and do that multiplication. Take away 20 times 48, that's take away 960 over 10. So we get here x equals 32 plus or minus the square root of, now 1024 take away 960, That gives us subtracting 64, which is, of course, a perfect square, over 10. Okay, let's just finish up over here. We have x equals 32 plus or minus the square root of 64 over 10. So we have x equals 32 plus 8 over 10. The square root of 64, of course, is 8. And x is equal to 32 minus 8 over 10. 32 plus 8, that's 40 over 10. That's 4. 32 minus 8, that's 24 over 10, which reduces to 12 over 5. And you will notice that we got exactly the same solutions. X equals 4, x equals 12/5 that we got from the method of factoring. X equals 4, x equals 12/5. Okay, so if you can't factor, you can certainly still solve nonlinear systems of equations. X equals 4, x equals 12/5. Then, of course, you would go on and find the y values that correspond, and you would have the solutions to the system. X squared plus y squared equals 16. X plus y equals 8. Okay, this is a circle, and this is the equation of a straight line. Let's first try to do it graphically. The circle has center at the origin and radius 4. The line, if you set y equal to 0, the x-intercept is 8. 3, 4, 5, 6, 7, 8. If you set x equal to 0, the y-intercept is 8. We are looking for points of intersection of these two graphs, and of course doesn't seem to be any from the picture. Something like this, of course, we can sort of rely on our picture. Okay, this is fairly accurate. We would expect, therefore, when we try to solve this system of equations algebraically, that there should be no real solutions. Let's actually do that just to see what happens. Once again, solving by the method of substitution. This is the only logical thing to do when you have a second-degree equation and a first-degree equation. In a moment, we'll consider two second-degree equations, and then you can either use substitution or elimination. Okay, but when you have one second-degree and one first-degree equation, substitution is really the only way to go. Here, solving the second equation, let's say for y is equal to 8 minus x, and we will now substitute that into the first equation. Okay, x squared plus y squared equals 16. X squared plus 8 minus x, parentheses squared, equals 16. X squared plus, squaring this out by FOIL, 8 times 8, that's 64. Minus 8x minus 8x minus 16x plus x squared equals 16. Let's see, collecting like terms, we have 2x squared minus 16x plus 64 minus 16 plus 48 equals 0. The x squared and the x squared gave me 2x squared minus 16x. Bring the 16 over. Minus 16 from the, taking 16 away from 64 gives me the 48. Okay, trying to factor this, I first see that there is a factor of 2 in common here, all the terms, so I can pull it out. X squared minus 8x plus 24. We're looking to solve this quadratic equation. If you're good at factoring, you can sort of go through the possibilities very quickly and say there are no two integers that multiply to 24 and add to minus 8. Okay. If you can't do that, we can certainly try it by the quadratic formula. We have x squared minus 8x plus 24 equals 0. We're matching that up to ax squared plus bx plus c equals 0. A equals 1, B equals minus 8, C equals 24. So we get x equals minus b plus or minus the square root of b squared minus 4ac over 2a. Now, minus b.